our next speaker is Manuel Bibes. Manuel Bibes, this is the second privilege of the day. No, by chance, he belongs to the same institution as the previous speaker, which is highly unusual, right? And he's one of the leading minds in the field of complex oxides, correlated oxides, and he is also a pioneer in bringing all these spintronics concepts in the field of correlated oxides. He's a very successful researcher in this area, right? There are many, including myself, following him, right? And he has succeeded in very exciting ideas in designing spintronic scenarios in these interfaces between oxides. So his talk will be about oxide spintronics. And Manuel, the floor is yours.
Thank you very much. It's too much, very nice thoughts, too many nice thoughts from you, Jacobo. Thank you very much to you and the organizers. I'm happy to be here, but I would be even more happy to be with you in Madrid or somewhere, finally. But maybe next time we can actually meet. I think we see the light at the end of the tunnel, as they say. So I'm going to share my screen. Let me see if I can do that. I am going to share my screen. Okay, let me see. I can share. Okay, and this is my presentation. Is this one? It's this one. Okay. Do you see the screen?
Yes. Yes, we do.
Do you see the people on the camera on the right hand side, or you just see the PowerPoint?
Yeah, we see the arrow.
You see the arrow. Okay, that's good. Okay. All right. So thanks a lot again. So I'm going to try to give you a brief introduction to Oxide Spintronics. So my name is Manuel Bibes. I'm from the CNRS-Thales lab, like my colleague Julie. We actually have our offices just less than 10 meters from one another in the lab, but she was at home, and today I'm at home as well, still working. So this is the work that we've been doing with many collaborators from mostly in France and in Europe over the last maybe 10 to 15 years. So I don't have time to thank everybody, but here you have the name of the people who in our lab were doing all the hard work with us, especially the PhD and postdocs. And here we go. So this is the outline of my talk. So I will have three parts. I will start with quite basic things that you may all be familiar with, tunneling, magnetic tunnel junctions. And I will try to show you that bring some interesting new features, functionalities into these tunnel devices. In particular, when one incorporates ferric degrees of freedom in the barriers. The second part, I will be quite brief about electric field control of magnetism with multiferroics. This is a very big field of its own. Just touch upon a couple of results, and I will introduce the one device proposed recently by Intel, which I think is very relevant for our own research and for the whole community following this school as a whole, and show some results on the most recent research using oxide in spintronics, basically spin orbitronics, taking advantage of spin orbit coupling in oxide two-dimensional electron gases, 2DEGs, for spin to charge interconversion. And the very last few slides will be about how to control the spin to charge conversion by ferroelectricity. So kind of making the link with the previous topic. So tunneling is quantum mechanical phenomena. You're probably all familiar with that. Here you have two metals separated by thin insulators, and the wave function of the electrons has an exponential decay when it crosses the insulator. This is tunneling. If the insulator is not too thick, there is a finite probability for the electron to have a finite amplitude when it reaches the metal number 2. So this is the equation of the current in these tunneling devices. And I don't want to get into details, but there's these two terms that are very important. One is telling you that the amplitude of the tunneling current is going to depend on the density of state near the Fermi level at both interfaces, at the interface between the first metal and the insulator, and at the interface between the second metal and the insulator. And there are these matrix elements, which are functions that typically depend exponentially on the thickness of the barrier, which has to be kept in the range of a few nanometers, on the effective mass in the tunneling regime, which is different from the effective mass in the electrodes, and also on the barrier height. So I will show you some examples of devices involving oxide, of course, where the tunneling current is modulated by the density of states, and in the second part by acting with external stimuli on the tunneling matrix elements, mostly by playing with by varying the tunnel barrier height. So in magnetic tunnel junctions, this is a typical TM marker from back in the days, 1995, 1997. Cobalt, aluminum oxide, cobalt iron tunnel junction, where we had very square switching, and here about 30% of TMR. The TMR occurs basically because you have different resistance states when the magnetization of the two electrodes are antiparallel to each other, and this occurs in this small range of magnetic field. The mechanism for the TMR was proposed by Michel Julier, who is actually French, and he made one of the very first works on TMR, and he published a paper in 1975 where, I mean, the results were not very, very clear, but he had the intuition of the mechanism of the TMR, and basically he made this. He had this insight that the TMR is going to depend on the spin polarization of the electrode. So the spin polarization is basically the relative fraction of spin up electrons at the Fermi level with respect to spin down. So you can define this like this, and the rho here is the density of state for majority spin up, minority spin down electrons. And basically, if you have two similar electrodes, or two electrodes with the same spin polarization, in the parallel state, you will have a large current flowing corresponding to the spin up electrons, and in parallel, you will have a small current corresponding to spin down electrons. But overall, because this is you have a connection in parallel, you will have a rather large current and low resistance. When you flip the magnetization of one of the electrodes with respect to the other, you flip the sign of the minority carriers in one electrode become the majority carriers and vice versa. And so at the end of the day, you have a lower current and larger resistance. And so this is why when you switch the magnetization, you have a TMR effect. So the TMR is proportional to the product of the spin polarization P1 of metal 1 and spin polarization P2 of metal 2 over 1 minus P1 times P2. So of course, you can directly see that if the spin polarization approaches 1, meaning that you have only one type of electrons, only spin up electron, for instance, then this diverges, and you are going to get a very, very large TMR. So in normal ferromagnets, back in the days, before the discovery of MgO tunneling barriers, normal ferromagnets had spin polarization of about 50%, more or less. And this gives you TMR on the order of 50–70%. But there's another specific family of ferromagnetic metals called half metals that were conjectured in the 80s by de Groot. And these half metals have electrons at the Fermi level of only one spin polarization, only spin up, for instance. And then there's a gap for the other spin direction. So if you use this material, these half metals, you are expecting to get almost infinite TMR. So these are quite rare. And in fact, many of them are oxide. So this was probably the first steps of oxides into the realm of spintronics. And so here I've listed for you some magnetic oxide that have been predicted to be, or even measured to be half metallic. And many of them are actually quite difficult to grow, like these double perovskites. You cannot anticide between the iron and molybdenum, so this, is not good for the magnetic properties. And these manganites are correlated oxide, as you probably know. They are relatively easy to grow by sputtering or PLD, and so they've been used the most in the early years of Oxide Spintronics. So here, this is a phase diagram of this compound. There's a whole family of these tandem strontium manganites, but only in this range, which is quite broad, of composition, you have ferromagnetic behavior, and the TC is at most about 360K. And in this range, you have half metallic behavior, and this is a natural consequence of double exchange. So the spin polarization was measured by spin polarized photoemission, and it was found to be at least 90%. And then people, including us, started to use them as electrode internal junctions. And you can see here a TM image of one of such junctions with two LSMO electrodes separated by an epitaxial tunnel barrier of strontium titanate. And here we could measure a very high TMR of almost 2000%. So this was more than 1 order of magnitude higher than any TMR measured at the time. And so it was really kind of qualifying these manganites as very good, very interesting materials for spintronics. And you can calculate the spin polarization from the TMR, and we got something in excess of 95%. So really very high. So these manganites can be used as almost perfect sources and detectors of spin currents. And you can use that to gain insight into the electronic structure of materials, for instance. And just in these symmetric tunnel junctions, LSMO, STO, LSMO, if you measure the TMR as a function of the bias voltage that you apply between the first and the second electrode, basically, as you do that, you are sending fully spin polarized electrons into the band structure of the second electrode at a given energy that corresponds to this bias voltage that you apply. And so in principle, if you remember, you have a band gap in this in the minority states for these half metals. So in principle, as long as your electrons arrive at an energy lower than this lower than the bottom of the connection band for minority spins, basically in the minority band gap, you have a fully spin polarized current, and you basically should observe an infinite TMR. In practice, it's not like that because you have inelastic processes that reduce the spin polarization. But then when you enter the gap, you exceed the gap, then you start to see a maximum and then a decrease, which we saw in these experiments. And it was quite reminiscent of predictions from a few years before by Bratkowski. So you can do, let's say, spin-dependent spectroscopy with these very good half metals. So this is what I wanted to say about using density of state effects to achieve large TMR. Now I'm going to talk about how you can play with what happens in the barrier itself. So now we were talking about the electrode, now we are going to talk about the barrier. And then you play with the matrix elements. And because you have this exponential factor, anything that you're going to do to modify, for instance, the barrier height is going to have a very dramatic effect because of the exponential factor here. So now I want to introduce, to speak about these ferrocordons. So I've talked already about ferromagnets. Ferromagnets are members of one family of ferric systems, but you have in fact 4 types of ferrocordons: ferroelectrics, ferromagnets, ferroelastics, and ferrotoroidics. Most importantly here, I will talk about ferroelectrics in addition to ferromagnets. And in ferroelectric, just like in ferromagnets, you have a hysteretic dependence of the other parameter, which here is the polarization, which is the sum of all the electric dipoles in your material, if you wish. And it depends hysteretically on the electric field. You can have also multiferroics, as you know. So in these multiferroics, you combine, for instance, ferroelectricity and ferromagnetism. So you have these 2 hysteretic dependencies in principle. And you can have also magnetoelectric coupling, which allows you to manipulate magnetization by electric field, for instance. So I call these intrinsic multiferroics, but you also have artificial or interfacial or multi-phase multiferroics, where basically you have coupling at the interface between a ferromagnet and ferroelectric, for instance, and you have magnetoelectric coupling here at the interface between the two. So these ferric materials, of course, are good for data storage. You have lots of different types of memories using ferromagnets and using ferroelectrics. And an efficient way to read out the stored data stored by the state variable, the order parameter, polarization or magnetization, is to do tunneling, because tunneling is very sensitive to all these things, to all these parameters. So now let's talk about magnetic junctions again, but we will put the ferromagnetism in one electrode, and then not in the other electrode, but in the tunnel barrier. So we have two ferromagnets. One is a metal, one is an insulator. And because when the barrier is made of a ferromagnetic insulator, in fact, you don't have just one tunnel barrier height, but two, depending on the spin. And so because the tunneling current depends exponentially on the barrier height, you will, if you have electrons incoming from a non-magnetic source, you will generate this spin up and spin down electron with tunnel with different rates. And so you will filter spins out, and eventually you will reach a very highly spin polarized current. So this is why these junctions are called spin filters. And then this spin polarized current can enter the ferromagnetic metal here. And just like in the previous case, depending on the alignment of the magnetization between the barrier and the metal, you will have a low or high resistance. And so you will have a TMR effect. So this was the first indication of spin filtering were reported by Modera in superconducting tunneling junctions. So I don't want to go into detail, but a few years later, well, actually 12 years later, this paper reported the first, let's say, TMR-like evidence for spin filtering. And there the junction was made of europium sulfide, that was the ferromagnetic insulator, and the ferromagnetic metal was gadolinium, and then there was gold on the other side. So you see the TMR was quite high, with a funny shape, but more than 100% of TMR. And so I think we started to work on that already maybe in 2002, so 2001, 2002. We started to work with ferrimagnetic and ferromagnetic insulating oxides as a tunnel barrier, and we combined them with manganite, for instance, and we found TMR due to this spin filtering effect. So the material we used was spinel ferrite, for instance. Nickel ferrite has a TC above 800K, so it should be quite promising. We had probably some defects in our devices, so we could see some TMR at low temperature, but not at room temperature. But then a few years later, actually the same year, there was a group also in Paris-Saclay at the CEA who grew this film by MBE. They could observe a small TMR at room temperature. So this works. The effects are not very spectacular, but this works. Probably the quality of the material is not sufficient to produce these very, very large effects. Then we started to work with barriers, insulating barriers with another embedded ferric order parameter, ferroelectricity. And so then there is a number of very exciting phenomena that can arise. And here there's a missing reference, because actually the first concept of this, after very early results from Ezaki in the 70s, this model that I'm going to explain to you now is from Mesgenit symbol. So I apologize, I don't have the reference here. Basically the model is as follows. So let's say you have a tunnel junction, and you have the barrier is made of ferroelectric material, so very thin ferroelectric. And you have two electrodes. They don't need to be magnetic. Let's make them non-magnetic for simplicity, but they need to be different. They need to be made of two different metals, which have different carrier densities and therefore different screening lengths. So when the ferroelectric is pulled towards the metal, you're going to have some polarization charges, and they are going to have to be screened by the electrons in the metal. And so depending on how good the metal is, it will screen very well or not so well these polarization charges. And if the screening is very good, basically you will have only a small additional built-in potential that will occur at the interface. If the screening is bad, then you will have a large screening length, and so you will build up an extra potential. And when you switch the polarization from pointing to the good metal to the bad metal, basically the potential profile that you see here is going to be modified. But most importantly, I mean, for simplicity, you can think it this way. Think about it this way: the average barrier height, which is shown in purple, is going to vary. So it's going to depend on the direction of the polarization. And as I told you, the tunneling probability is proportional to the exponential of the square root of the barrier height. So any change in the barrier height is going to give rise to a large change in the resistance, and we call that the tunnel electroresistance. So, then we started to make tunnel junctions, to make samples, and we were working with Neil Mather in Cambridge for that. And this was mainly the work of Vincent Garcia. And here we have a bottom electrode of LSMO. I think you know now that this is one of our favorite oxide material. And then we have a thin layer of barium titanate, which, as you know, is a ferroelectric. And here it's very thin, just maybe 7 or 8 unit cells, but it's grown on neodymium gallate, which is a substrate that imposes a quite large strain. And everything here is fully strained up to the barium titanate. And so the barium titanate has a strain of about 3%. The iron on top was deposited by sputtering. So it's a ferromagnet, of course. LSMO is also a ferromagnet, but what I'm going to show you now does not involve magnetism at all. So the first thing we did was to try to check if our very thin barium titanate was ferroelectric. So for that, we use a technique called piezoresponse force microscopy. This is a scanning probe technique, which we can use to probe, basically to image ferroelectric domains. And also you can use the same tip, which is conductive, to apply a voltage and basically to pole the material along different regions and thereby writing artificial domains. So we did that on different samples, and this is an example for a 1 nanometer barium titanate sample. And you can see here PFM images of domains that we wrote with the tip. And we can switch them back and forth. Everything looks nice and okay. And they are stable over time, which was not a given because this barium titanate was very, very, very thin, just 1 nanometer. So we did that for 1, 2, and 3 nanometer samples. And then we use another scanning probe technique, which we have in our lab, which is called Conductive AFMM microscopy. And we scan we measure the local resistance across these domains. And we found that the resistance was very, very different, depending on whether we were sitting on top of a domain with the position pointing up or down. And you see that we have very large contrast, up to 75,000% here. So we confirm this giant tunnel electroresistance in ferroelectric tunnel junctions. And you can see here that the effect increases strongly with the thickness, which is also what you expect from theory. So then we moved to making solid state ferroelectric tunnel junctions, where we deposited dots of top electrodes. Here, typically we work with cobalt, but then we studied other metals. They don't need to be ferromagnetic again. And we made devices with dimensions ranging between around 100 nanometers to 1 micron. And then we made experiments, basically contacting them with a conductive AFM tip. So the tip is used to apply a voltage to pull the ferroelectric below the junction, to measure the resistance, and also, but I won't have time to show these results today, to image the ferroelectric domain structure in the barrier below the top electrode. So here, this is PFM, so piezoresponse phase and amplitude loops, which confirm that the barium titanate below the top electrode is ferroelectric. And then we can measure the resistance as a function of the voltage that we apply to the junctions. We apply voltage of different amplitude, and in between we read the resistance level with a small voltage of here 50 millivolts. And you see that we have a large hysteretic dependence with two extreme resistance states that are different by more than 2 orders of magnitude. And in some devices, we have a difference of up to maybe 4 or 5 orders of magnitude. So we have a confirmation of this tunnel electroresistance effect in the solid state devices. We show that they can be relatively fast. They work at low dimensions. And also, this probably resonates a bit, echoes a bit some of the things that Julie discussed before my talk. We showed that these tunnel junctions, in fact, you can stabilize any intermediate resistance state. You don't have access to just these two extreme states. You basically have access to a pseudo continuum of states in between. And depending on how intense the voltage you apply is, but also on how long you apply it for. And basically, this defines a device called a Merister, which are electronic analogs of the synapses in our brains. And so, collaborating with Julie, we implemented a number of operations, including the demonstration of spin-dependent, spike timing-dependent plasticity with these junctions. And we also showed that the resistance level was here determined by the ferroelectric domain configuration. So now back to Spintronics. So here I'm going to show some results in which we combine the spin filtering effect, which you have when you work with ferromagnetic barriers, and the tunnel electroresistance effect, which you have when you work with ferroelectric barriers. And for that, we needed an intrinsic multiferric material that was at the same time ferromagnetic and ferroelectric, and these are extremely rare. And this is a Venn diagram which I constructed a few years ago, inspired from one that was published in that paper by Ehrenstein, Mather, and Scott. This is for oxides, and here you have magnetic oxides, and you have polar oxides, and just here in the middle you have materials that are at the same time ferromagnetic and ferroelectric. And basically we use this actually it's at the intersection between these purple and orange circles. Okay, so we worked with this compound lanthanum bismuth manganite, which after a lot of efforts we could show could be at the same time and even at low thicknesses compatible with tunneling, ferromagnetic and ferroelectric, as you can see here. And then we used it as a tunnel barrier in our junctions, again with LSMO, and then with gold as the top electrode. And we saw at the same time TMR coming from the spin filtering effect due to the ferromagnetism in the tunneling barrier. And then we also saw tunnel electroresistance. You see these two curves are collected after polling the barrier in one or the other ferroelectric states. So we had a 4-state memory in which the different resistance states, the 4 resistance states were encoded by the 2 other parameters of the multiferric barrier. So this was probably the first Spintronics multiferric device, really at the beginning of the booming era of multiferrics. Right, so I'm finished with this first part. I'm going to move to the second part, in which I will talk again about multiferrics, but now to control magnetism by electric field, which is, let's say, the main reason why they were rediscovered in the beginning of the 2000s. So one device that we proposed and others proposed that could be done with multiferrics is this very simple one that I'm going to show here. At the time, we called it a magnetoelectric random access memory, I think. So here, basically, you have a tri-layer that can be a magnetic tunnel junctions, 2 ferromagnet, and a spacer, which can be insulating. It can also be a spin valve with a GMR. So the pink layer here can be a metal as well. And this is sitting on top of a multiferric layer. And then you have a bottom electrode at the very bottom. And in the multiferric, you have a coupling between the polarization and the spins. Here, the multiferric is an antiferromagnet because so far, I don't think no one has really shown convincingly that there was a ferromagnetic and ferroelectric multiferric at room temperature. So the best material we got is bismuth ferrite, which is a good ferroelectric and a good antiferromagnet, both at room temperature. So you need to have some kind of exchange coupling between the spins in the antiferromagnet, typically at the interface between the antiferromagnet and this bottom ferromagnetic layer here. And then when you switch the polarization by applying a voltage, the plan is that when the polarization switches, the spins are going to switch due to magnetoelectric coupling. And because of the exchange coupling between the spins and the magnetization of this layer is going to switch as well. And then the resistance will change. And then you will be able to, let's say, control the resistance in a hysteretic way with voltage. And this amplitude between the two resistance states is going to be that of your TMR tunnel junction here. So there's a number of prerequisites before one can do this, and this possibly not an exhaustive list. So you need to have exchange coupling at room temperature between your bismuth ferrite, let's say, and your ferromagnet. You need to have no leakage through the ferroelectric. This is quite challenging. You need to have TMR or whatever spin device you want to have on top, TMR or GMR system. And then you need to be able to have magnetoelectric coupling to switch the spins when you switch the polarization. And this is extremely challenging. So this paper is one of our most advanced efforts to reach this goal. So we solved a number of these issues, but we did not have a really reversible switching effect. We did see the switching though. And then the most advanced work, and this is maybe not the most recent, but this is the work that was done by Ramesh in Berkeley. You may be familiar with his work. So he worked with bismuth ferrite, and then he has cobalt iron on top. And then he makes these GMR layers with a copper spacer and then another cobalt iron layer. And then he takes advantage of a specific switching process of polarization in bismuth ferrite, which is called a two-step switching process, which in principle allows to switch the magnetization, the weak moment of the bismuth ferrite, because bismuth ferrite is an antiferromagnet. I mean, it's a complicated antiferromagnet because it has a spin cycloid, etc. But you can, for simplicity, let's assume it's an antiferromagnet, but it also has a small weak moment. Okay, it's a weak ferromagnet, if you wish. So as you do that, you can switch the weak moment of bismuth ferrite by electric field. And these are some beam images at the cobalt edge that show that the magnetization of the cobalt can be switched one way and back by applying negative or positive voltages. Okay, so now they are really working very hard, and there's a collaboration with Intel that I will mention, on which we participate as well, and trying to make this in the shape of actual devices, and having a very large endurance for the switching multiple times. I mean, multiple thousands or millions of times in multiple. And this is basically the resistance as a function of the, in blue you see the resistance as a function of the voltage. That really looks like the curve of the sketch I was showing you a few slides back. Okay, so I want to say a few words about this, this Intel device. This is called MISO device. And MISO stands for magnetoelectric spin orbit, and it's some kind of transistor. And this was proposed, this was published in 2019, but they had a paper on archive that was put there maybe in 2015 or 16, so several years before that. And it's a very interesting new device because it's a non-volatile logic device. And here the non-volatility is provided by ferromagnetism. The core or the heart of the device is a ferromagnetic element. And then it is concatenable, chainable, can be used as a majority gate. There's a lot of advantages. And the way it works is basically you have the ferromagnet sitting on the input on top of a magnetoelectric material, can be bismuth ferrite. And then at the output, you have a spin orbit material. So the input is basically what I was showing you just a few slides ago. You will apply, you will charge the you apply current here, so you will charge the magnetoelectric, the ferroelectric, and eventually you will switch it. And then if you have magnetoelectric coupling, this will switch the direction of the magnetization in the ferromagnet here. So this is how you write this non-volatile information. And then how do you read? So you send a current through the ferromagnet into this spin orbit element, which sits below. And then this spin current, so the current becomes spin polarized, so it carries a finite spin current. The spin current enters the spin orbit material and then is converted into a transverse charge current whose polarity, basically of sign, is going to depend on the direction of the magnetization. So if the magnetization is pointing towards me, you will have, say, a positive output current, and pointing towards you, it will be a negative charge current. So you can read this paper and look at the very long supplementary material where the Intel guys have been doing a lot of simulations and argue that you can save a lot of power by implementing this compared to CMOS, typically 30 times less than CMOS. And the key is to use an electric field to switch an insulator, and as a result, the magnetization of the ferromagnet. And magnetoelectric switching, they say, is much more efficient than spin orbit torques or other methods to switch magnetization by up to a factor of 1,000. So it's really a very big effect, very big difference. So the device has to operate with 100 millivolts. So basically, you need to be able to switch the magnetoelectric with 100 millivolts and to output 100 millivolts, which is extremely challenging. So this is giving me a transition to the second part, the third and last part of my talk, in which I will try to show you that oxides can also have something to say in this business of spin-to-charge conversion, and they can, in fact, be very, very good spin-to-charge converters. So this is the last part of the talk, and spin-charge interconversion with oxide 2DEX. So oxide 2DEX, probably you all know about this. This is the most paradigmatic system. This is the LAO STO system. And if you don't know about that, this was a very arresting result from 2004 by Harold Wang when he was in Japan. And basically, he grew a thin layer of lanthanum aluminate on top of strontium titanate. And although these two materials individually are very good insulators, when one is ground on top of the other, you get a conductive behavior. Basically, you have a two-dimensional electron gas that appears at the interface. A few years later, 2007, we imaged actually the two-dimensional electron gas. We made a conductive atomic force microscopy image of the gas in cross-section, and we confirmed that it is very, very thin and very conductive. Thickness was a few nanometers. Here we have some convolution effect by the tip, so it's probably on the order of a few nanometers, 2-3 nanometers maybe. And this 2DEC has a lot of interesting features. It has a quite high mobility at low temperature. Here you see we have 3,000, but in some samples, some authors have reported, I think the maximum is around 140,000 by a group in Denmark. It is superconducting. This was discovered for the first time by Johan Mannert and Jean-Marc Ruscon. And it is also gateable because it's a 2D system. So if you apply a backgate, you can accumulate and deplete carriers with a large efficiency. And this does a lot of things to the 2DEC. Basically, you can turn superconductivity on and off by applying a gate. You see here that here you have superconductivity, and then you can kill it if you apply a negative gate voltage beyond here, minus 150 volts, for instance. And finally, and that's the most important for what I'm going to show later, there is a sizable Rashba spin-orbit coupling. And I will explain what this is in the next few slides. But this was discovered again in the group of Jean-Marc Ruscon in collaboration with Marc Gabet from Orsay. And this Rashba spin-orbit coupling was showing up as an effect in the magnetoresistance called weak anti-localization. And then through fittings, these authors were able to extract the Rashba coefficient, which is here alpha. It's on the order of a few tens of milli-eV angstrom if you want to compare with other systems. It's not very, very large, but it can do a lot of things, as I will show you, and it depends strongly with the gate voltage. So what is rush-bar spin-orbit coupling? So it's a manifestation of spin-orbit interaction, which occurs in systems with symmetry breaking, inversion symmetry breaking. So typically at a surface, at an interface, or also some ferroelectrics can also display rush-bar spin-orbit coupling. And as a result of this inversion symmetry breaking, this rush-bar Hamiltonian enter the systems. And basically, as you can see here, it wants the spins and the momenta to be perpendicular to each other and also perpendicular to Z, which is the direction normal to your surface or interface. And as a result, you have a lifting of the spin degeneracy and a shift of the bands, the parabolic bands, along K. And if you take an energy cut here, you see Fermi contours that are splitted, and you have the spins that are curling clockwise or counterclockwise along the contour because the spin is always perpendicular to the momentum, okay, perpendicular to K. So these rush-bar systems are very interesting because they enable a number of cool spin-orbitronic effects. So let's see what they can do. So if you inject a charge current into such a system, basically you are going to shift a little bit these two Fermi contours. And because they have this spin momentum locking, in this contour, this will generate an extra density of spin up. And in that smaller contour, an extra density of spin down, but smaller. So all in all, you will have a finite generation of spin density. And these spins will be transverse to the current. So you apply a current, you generate a magnetization, if you wish, transverse to the current. This is not a Riemann magnetization. It goes away when the current goes away, but it increases linearly in amplitude as you increase the current. This is called the direct Edelstein effect, and it was predicted in these papers. You have the converse effect, which is the inverse Edelstein effect. So here you are going to inject a spin current with your method of choice. I will show one in the next few slides. And as you do that, basically you are going to shift the Fermi contours again because you are putting excess spin up here and there. And so they shift in opposite direction, but not by the same amount. And so this creates a charge current. So you are conducting a spin current into a charge current. So you can do things both ways. And this is the inverse Edelstein effect. And this was discovered and formulated much more recently. And this is a paper from our group by Carlos Rojas with Albert Fert as the lead author. So you may be familiar with the spin Hall effect and inverse spin Hall effect, where you also convert charge and spin currents. They have the same dimensionality, 3D to 3D, 2D to 2D. Here, basically, in the inverse Edelstein effect, for instance, you are injecting a 3D spin current, and the charge current that is produced is 2D. So the ratio of the two as the unit of a length, lambda, and this is proportional to the rush-bar coefficient. I mean, the bigger the separation between these two contours, which is what your rush-bar coefficient measures, the larger the effect. And also, and very importantly, it is proportional to the momentum relaxation time. So if you have a system with a very large rush-bar, but a very short momentum relaxation time, like metallic interfaces, like silver bismuth, in which this effect was discovered, you may see some effect, but it's not as large as you may expect from the large rush-bar coefficient, because in metals, the tau is very short, just typically a few tens of femtoseconds maybe. So we did spin to charge conversion experiment in our LAO STO2 decks in collaboration with the group of Laurent Villa in SpinTech. And to inject the spin, we use a technique called spin pumping FMR. So we have a ferromagnet, which we grow on top, and we put this in a sample in a microwave cavity, and we scan the magnetic field until we reach a resonance condition for the magnetization, at which point the magnetization starts to process. And as it does process, a finite density of spin angular momentum, that's basically spin current, is ejected from the ferromagnet and injected into the 2-deck, where we expect it to be converted into a 2D charge current by the inverse Ehlers-Danlos effect. So we measure the ferromagnetic resonance. This is a measure of the ferromagnetic resonance signal, if you wish. We see it occurs a little bit below 1 kilo Oersted. And just at the same field, if we measure the voltage, we have two contacts just to measure the voltage, and we see a peak in the voltage appearing just at the resonance. And this peak switches sign when we switch the direction of the magnetic field. Basically, we change the direction of the magnetization, we change the sign. So we really have a conversion from spin to charge, okay? And we can use that to read out the direction of the magnetization in the meso device. So this is a clear indication of the inverse Ehlers-Danlos effect. And what was very striking in these results is, first, in fact, the effect is very large in these two decks, very, very large, and we'll come to that. But also when we apply gate voltage, so basically we have a back gate and we accumulate or deplete electrons. Basically, we put the Fermi level at different positions in the band structure, and we'll also come back to that. We see that the amplitude and the sign, even the sign of the effect changes. And this is really a very unique feature of this STO2 decks. So we can quantify the efficiency to see how good we are compared to other systems. So we need to quantify the spin current that we inject. We know how much charge current we produce, and we extract lambda values on the order of a few nanometers, which is larger than other materials, even topological insulators, although I must say that this was at low temperature. And in fact, the values that we get are quite compatible with what you would calculate from the Rashba coefficient, a few tens of millieV angstrom, and tau on the order of 1 to 10 picosecond. So here you see that the effect is large, despite the relatively low amplitude of the Rashba coupling, because we have a 2-deck and we have a much longer scattering time than in metals. Okay. So we work with slightly different samples a few years later. Basically, we define the 2-deck not by depositing an epitaxial layer of LAO, but by growing a thin layer of aluminum that becomes aluminum oxides. And this is enough to create a 2-deck. So this is done at room temperature. This is much easier. And the current densities in these 2-decks is slightly higher than in the 2-decks with LAFTO, meaning that the Fermi energy is higher. And this will be important in the next few slides. So we do the same kind of experiment, and we also see a strong spin to charge conversion signal, also changing sign. And here we have something even more complicated with several changes of sign. And we believe that our understanding is that the LAO results corresponds to this range here. So we have positive effect, change of sign, and then the negative maximum, negative minimum, and we were stopping here. Here, because we start with a higher current density, we are able to probe this additional regime. And also importantly, here we have a lambda which is larger, up to maybe 25 nanometers. So why does this inverse Ehlers-Danlos effect change its sign? So this has to do with the band structure. And this is some R-plus data from colleagues from the University of Geneva, on which we have plotted tight banding calculation from the University of Halle, from Annika Johansson, Børge Goebel, and Ingrid Mertig. So this is the Fermi surfaces at the Fermi level. So you see basically you have two types of Fermi surfaces. You have a number of, let's say, circular Fermi surfaces. This one is the most visible, but also you have two ellipsoidal Fermi surfaces that are not so visible, but I think if you have good eyes, you can see clearly that it's there. So it's this elliptical shape, and it is there's another one here. So this is typical. This was known, and you can see the dispersion curve. So we have basically light bands, and then you have a heavy band, and they cross. Okay, and when they cross, a lot of things can happen. So they cross here. You can see that they cross. They cross if you look at the dispersion along 100, but you can also make a cut here and look at what happens along 110. They also cross, they interact with each other, and you can also look at along this specific direction, which we call delta, where basically you see we have interaction between three bands here. And this gives a very rich physics. And from theory, we can calculate that here we have a topologically non-trivial crossing, a little bit like what happens in topological insulators. So we expect that when the Fermi level is going to sit there, we're going to have a larger spin-to-charge conversion. So our colleagues from Halle computed, using this band calculations, the efficiency of the spin-to-charge conversion for each pair of bands that I've shown you, and then this is the sum. So I'm going to take you through that step by step. I don't know how much time I have left, Jacobo, 5 minutes?
Yeah, you can take 5 minutes. Yeah.
Okay. I think I need 5 minutes and then I'll be finished. So I'm going to take you slowly through this. So let's start at low energy. So we are, let's say the Fermi level is here. We just have one band, the purple one, which is populated. And we have this circular contours. Actually, there are two there that you cannot see because they have a very weak Rashba splitting. And therefore, the efficiency of the Edelstein effect is very small here. Then we increase the Fermi energy and we start to enter the second band, which is shown in green. We have a slightly larger effect. And then we arrive here at this point where we start to populate this orange band, which has a heavy character. And this band has an opposite sign for its Rashba coefficient. And so that's why we see a maximum and then it starts to decrease because you see the orange band has a negative contribution compared to the purple and the green. And we start to see here a little bit already the interaction between the bands and we see the splitting due to the Rashba spin-orbit coupling. And then we enter this interesting regime where we have a strong interaction between the bands and the maximum Rashba splitting. And you can see here the colors here, blue and red, correspond to the direction of the spin pointing, let's say, to up or down. Okay, so this is maximum Rashba splitting, and we have here a negative maximum in the conversion. Eventually, we increase further. We reach this peculiar point that I described before, where this is this topological level crossing. We also have a maximum, and then we have other maximum and minimum. And now you can compare the sum of these effects shown in red with our experiments. And you see that we have pretty good agreement with all the maximum and all the maxima and minima here. So we really are able to conclude that the complex energy dependence of the spin charge conversion in the system, which can be really useful for devices, is caused by the unique band structure of this oxide 2-takes. This is a result of spin charge conversion with the same system at room temperature. So the effect is much smaller, but still, if you remember, I told you that we need output voltage of 100 millivolts with the Mezzo device. With this figure of merit that we extracted, we can in principle reach maybe 10 millivolts. So this is not, we are not quite there yet, but this is still quite encouraging. And the last 2-3 minutes, I want to show you some recent results that we've done in which we have incorporated one of these ferroic degrees of freedom that I mentioned before, ferroelectricity, into this business of spin to charge conversion. And this is quite appealing because basically at the interface between the ferroelectric and the spin orbit material, you are going to accumulate or deplete electrons. And so you are going to create a local electric field. And in the ideal case, the sign of this electric field will be switched when you switch the polarization, okay? And so if you have a Rashba state here, because this is a large spin orbit coupling material, you will switch the chirality of the Rashba contours, okay? If you remember the Hamiltonian, I did not insist on that. The Hamiltonian is a sigma, there's a mixed product between sigma, the spin, K, the momentum, and Z. And Z is the direction of the electric field associated with the interface. So if you switch the electric field, everything is reversed. The chirality of the spin contours is reversed. So basically, you can have one chirality or the other chirality as you switch the ferroelectric polarization. And then when you inject a spin current, you are going to collect a negative or positive charge current depending on the ferroelectric state. And so this can give interesting perspective for variations of the meso device in which you won't need to switch magnetization through this magnetoelectric coupling, which is notoriously inefficient. You just need to switch for electricity to control your Rashba states. And in principle, you have almost the same functionalities. So this is quite interesting in our view, at least. And so we demonstrated this effect with the same 2 decks, STO aluminum oxide 2 decks, but there we induce electricity in STO by applying a very large electric field. STO, as you may know as well, is very close to being ferroelectric. And just, if you replace 0.5% of the strontium ion in strontium titanate by calcium, STO becomes ferroelectric. Also, just a little bit of strain is enough to make it ferroelectric. And there's a few papers from the literature down to 1956 who show that if you apply a large electric field in STO, you stabilize a ferroelectric state. This is not fully understood, but this was observed by many groups. And so this is basically the polarization as a function of electric field at low electric field in this kind of system. So here we have a bottom electrode, which we use as one of our contacts, and the 2 decks, the other contact. This is expected, but then when we apply a large electric field, then we see the development of a very clean ferroelectric polarization loop with clear switching peaks in the current curves. We can study this as a function of temperature, and we find that the TC is about 50 K. This is exactly consistent with the result from that paper, for instance, from the group of Leudel, same polarization, same TC. And then, of course, we try to see how this ferroelectric-like state was going to influence spin-to-charge conversion. So I'm going fast because I'm running out of time. But basically, we see that we have a hysteretic dependence of the charge current produced in these experiments with the gate. So we have a completely different dependence with the gate that we had before, and we have here 2 remnant states, okay? And the efficiency of the effect also disappears at about 50 K. So this is another indication that it is probably driven by ferroelectricity. So I'm coming to my conclusion. So I hope I've shown you that oxides bring many new possibilities in spintronics. You have a bunch of materials to choose from. Half metals can give very large CMR. Ferromagnetic insulators, also large CMR due to spin filtering. Ferroelectrics as barriers give you large stone electroresistance. You can make neuromorphic devices out of them. Multiferroics can allow you to have these multiple state devices. And you can also use multiferroics to control magnetism by electric fields. Although efforts are still needed to make things really robust and reproducible over many cycles at room temperature. And in the final part, I showed you oxide 2 decks, which are very good material for spin charge interconversion. They have this unique gate tunability of the spin charge interconversion. And when you add electricity as a new degree of freedom in this business, really, we are very excited by that because we think it can open the way towards new types of spintronics devices that will be non-volatile, but without ferromagnetism. Really, the non-volatility would be provided by ferroelectricity, and this should be much lower power in terms of applications. Okay, sorry for going a little bit over time, and thank you very much for your attention. I can take questions.
Thank you very much. Thank you very much, Manuel, for the very illuminating talk. We go now to the questions. Let me start reading the first question concerning the first part of the talk. Has electron spin diffusion length ever been measured in LSMO or in any other oxide?
Okay, so yes. So in LSMO, I'm not sure. The spin diffusion length of, for instance, of 2 decks has been measured. We measured that a few years ago. And at low temperature, we find a value on the order of 1 micron. So it's not very large, but it's still decent. You can make, you know, like in-plane devices, like with non-local transport or planar spin valves. This is enough. About the spin diffusion length of ferromagnets, I think it was measured, but I don't have the number exactly in the top of my head, but I think it's quite small, a few nanometers in LSMO and transfer methanate maybe. Yeah, this you want to have a long spin diffusion length. You probably want to start with a material with a long mean free path, so high mobility, and so the 2 decks are materials of choice for that.
Thank you very much. Okay. In the ferroelectric tunnel junctions with cobalt, what happens to the magnetic states of the interface layer when you reverse the ferroelectric polarization? In principle, one expects this to be a sort of oxide, right?
So you mean that there's an oxide at the interface between the cobalt and due to a chemical reaction, oxidation of the cobalt?
Right, and magnetically, it could be different or not?
Yes, so that's a good question. So experimentally, I mean, in terms of functionality, if you use the same junctions with LSMO, barium, titanium, and cobalt, and you try to measure TMR, you do see TMR, negative TMR, maybe 20%. And it changes amplitude and even sign, depending on it can change sign. There was a paper by Manuel Bibes where he showed it changes sign with PZT barriers when you switch ferroelectric polarization. So you can change the amplitude and maybe even the sign of the TMR by ferroelectricity. So this is, if you wish, a consequence of an interfacial magnetoelectric coupling. Then, okay, so in TM, we did TM, and there is hybridization between the oxygen and the cobalt or the iron. I'm not sure we did cobalt, but I think we did the iron. And there is a change indeed of the electronic structure at the interface. And it also depends, I mean, band structure calculations reveal that the electronic structure of the interface, the iron-oxygen interface, depends on the direction of electric polarization.
Mm-hmm. Thank you very much. Let me check. Okay, what is special in these avoided band crossings in the 2-dimensional electron gases to increase the spin charge conversion? Is it the Rashba interaction which is made stronger?
Yeah, so that's a very good question. So no, actually not. What happens, I don't know, maybe I can zoom in so you should get better, yeah. So so what you see, so typically when you have, you work with band pairs. So you have one pair which has in principle a spin up and the other which has spin down due to the Rashba spin-orbit coupling. And like here on the left-hand side, you have maximum spin up and maximum spin down. Okay.
Manuel, you are not sharing. You are not sharing.
Excuse me. Okay, excuse me. I will share again. Let me go back here and share again. Share again my screen. Do you see the screen again?
Yes, we do.
Okay, I was trying to zoom in to show this better. So in a typical Rashba system, you have these two contours, and if you take for a given K direction, you will have maximum spin up for one band and maximum spin down for the other band. But here it's not like that. In fact, the expectation value of the spin is not maximum. It's not the same for one band and for the other band in a given pair. So you see, for instance, here we have a large dark blue contrast, but here we have almost zero spin here. This means basically the expectation value, if you wish, the length of the arrows in these sketches of the curling contour, the length of the arrow is almost zero. There's no arrow. And of course, then this gives rise to large conversion efficiency because one band is contributing in full and the other is not contributing in the other direction. So there's no compensation by the other band as you always have when you work with Rashba. In Rashba, you always have one band compensating for the other. So that's why in principle, it's better to work with topological insulators because you just have one contour. You don't have the other one which is compensating. And if you work with Rashba, you want to have a large Rashba coefficient, meaning that the inner contour is very small compared to the outer contour. So there's little compensation. But another way to limit the compensation is to work at points where the spin expectation values are not the same. And this is, I think, a very interesting feature. And this tells you also that about the richness of the band structure of these two decks.
I see. Very interesting. Could this potentially be done in systems with unquenched orbital angular momentum? Could this be a strategy to increase conversion?
Yes, actually, we published a paper with Ingrid Mertig and his colleague and our colleagues a few months ago, about the orbital Edelstein effect. So just like here, I was talking about spin or Edelstein effect and inverse spin orbit Edelstein effect. You can have also orbital Edelstein effect. So basically, if you wish, when you run a current, you will generate a transverse finite density of orbital angular momentum in addition to the generation of a finite density of spin. And the orbital to charge interconversion is much more efficient by a factor of 10 in our calculation. And I think this, so this is a new domain which is starting now. It's orbitronics. There's no more spin. It's just for orbitronics. And there's a number of nice results also from the group of Matthias Klawi in metallic system, where they found very efficient orbit torques that act on ferromagnets. So I think it's a good idea to try to find ways to maximize this orbital contribution, maybe with system with a finite orbital angular momentum. That would be some kind of ferromagnetic rush bar, but in which maybe the rush bar, the ferromagnetism will be mostly dominated by orbital magnetism, maybe. So these are clearly very interesting directions for the future. A lot of interesting physics to be done.
Thank you very much. Thank you very much. There is one more question by Saroy Das. Thank you for an excellent talk. In the last part of your talk, ferroelectric STO structures, is there any work on ferroelectric spin orbit materials where you can directly realize the sign change with electric field?
Okay, so in fact, we did see the switching of the conversion due to, we think, the switching of the ferroelectric polarization, but we are not completely sure that this is the mechanism that I described here. Okay, this mechanism, as far as I know, has not been demonstrated yet, and I think maybe you are alluding to materials which are intrinsically ferroelectric and have rush bar spin orbit coupling, and there's a few oxides that have been predicted to show this. But another interesting system, which is not an oxide, is germanium telluride, which is a ferroelectric semiconductor, which has a switchable rush bar spin orbit coupling. And the group of Riccardo Bertacco and Cristian Rinaldi in Milan, they have very nice results of controlling spin to charge conversion by ferroelectricity with germanium telluride at room temperature. Smaller effect than what we've seen, because these effects that I've just shown here are very, very strong. Lambda on the order of 50 to 60 nanometers. They have an effect which is a little bit smaller than platinum. So this is quite significant, and it can be switched by electric field and instrument. So they have a paper posted on archive on that, posted a few months ago, maybe in March.
Okay. I don't see any more questions, so I think we can stop here. Thank you very much, Manuel, for the very interesting talk and very illuminating overview.
Thank you.
We give Manuel an applause and see you next time.
Yeah. See you next time, for real, en vivo. Okay. Hasta luego.
Bye bye. Hasta luego.
Thank you.
luego.